This is Mr. Parvaiz with Henrico High School, and I'm going to show you a quick lesson regarding a roller coaster lab today. We're going to be connecting the idea of gravitational potential energy to kinetic energy. We're going to also be connecting this to projectile motion from previous chapters, and we're also going to tie it into how you're going to lose energy due to the work being done on an object by the force of friction. So starting off, I'm going to put a crude diagram up on the board about a roller coaster track, and instead of a car, we're going to be using a ball bearing to represent our coaster. So the first thing you're going to do is you're going to take a stand and put it on your table. You're going to be using that for support with your track. Feel free to use tape, whatever's best to connect your roller coaster track to the stand. As I said, it's a pretty crude drawing of a roller coaster track, but basically you should have it connected one end to the stand, the other end can be at the edge of the table. You may want to tape it down. You may want to tape the roller coaster track down at the end of the table. However, make sure that the pathway of the ball isn't blocked by any tape. So you're going to take a ball bearing and you're going to release it from the top. It's going to roll down. It's going to launch off from the edge of the table. So a couple of things you want to measure before you release the ball is you want to measure the height of the stand, because you want to calculate the gravitational potential energy the ball is starting off with. You're going to take the height of the stand and plug it directly into your gravitational potential energy equation right here, and you're going to calculate how much potential energy the ball has right before you released it. Remember, the mass of the ball is going to be in kilograms. The gravitational acceleration is going to be 9.81 meters per second squared, and the height is going to be in meters. So make sure if you measure it in centimeters that you convert it to meters. Two other things I'd like you to measure. Measure the time the ball spends on the track. So from release all the way to the point where right before it launches off the edge of the table. So I want you to measure the time it spends on the red track in my drawing. And I also want you to measure the distance of the red track. How long is your track? These are two things that we may use later on in the lab, so it's good that we have this information now. It may be useful later, it may not be useful. So make sure you measure the time the ball spends on the red track and the amount of distance it travels on the red track. Finally, the ball is going to get launched off from the edge of the table and it's going to hit the ground. Now make sure you measure exactly where it hits the ground on the first bounce, not the second or the third bounce, but on the first bounce, make sure you measure where it hits, because you're going to need to use that to figure out how far the ball landed. You're going to have to use that to measure the range of the ball. You can label the range R or D or X, whatever you prefer, but make sure to measure exactly where the ball lands on the first bounce. And of course, don't lose the ball bearing, so keep an eye on it. You're going to need it later on. You also need to know the height of your table from where you're launching it, because you're going to be using the range and the height of the table to figure out how fast the ball was going right at the edge of the table before it was launched off from the table. And how are you going to calculate this velocity the ball had right before it was launched off the table, which I'm labeling as v subscript x, or the horizontal velocity? Well, the first things first, you've got to calculate the time the ball spends in the air once it's launched off from the edge of the table. You've seen this kinematics equation before: d for displacement, d naught for initial displacement, v naught for initial velocity, t for time, a for acceleration of gravity. So it says d equals d naught plus v naught t plus 1/2 at squared. The d naught is 0 because now you're just using this equation to analyze the ball's motion right from the edge of the table all the way till it lands on the ground. So you can be using it just for the projectile motion part. The initial displacement is going to be 0. The final displacement is going to be how high the table is. Your initial velocity, initial vertical velocity is 0. Your acceleration is 9.8 meters per second squared. So just a reminder, I'm using all the y variables. I'm using variables that exist on the y-axis. The d naught is 0. The v naught on the y-axis is 0. The acceleration on the y-axis is 9.81 meters per second squared. So basically the equation simplifies to d equals 1/2 at squared. Make sure you show all of this work on your paper too, because you're going to be submitting it in to me at the end of the class. So now your equation is d equals 1/2 at squared. You're going to rearrange it to solve for t. You're going to rearrange it by taking the 2 to the other side by multiplying both sides by 2. And then you're going to divide both sides by a. And then finally you're going to take the square root to get to the square sign. So you can be solving this equation for t. You're going to be isolating t. When you rearrange it and isolate t, it'll look like this. The d is the height of the table. It's the displacement, the vertical displacement. The a is the vertical acceleration, which is the acceleration of gravity. So you're going to use 9.81 meters per second squared in here. Once you calculate the time the ball spends in the air, and you know how far the ball went, you're going to use the time and how far the ball went to get the horizontal velocity. So the range divided by the time will give you the horizontal velocity. You can write it as r, or you can write it as d, or x, whatever you prefer. So just be careful. There are a couple of times d shows up in here. So maybe it's best I use a r divided by t or x divided by t. But either case, now you can find out how fast the ball is traveling right here at the edge of the table. So everything on the right side of the table in purple is basically projectile motion. It's stuff from chapters 1, 2, 3, and 4. Now everything before, while the ball is on the table, is chapters 5 and 6. It's talking about energy, especially chapter 6 when it talks about potential energy. So now that you have the velocity at the edge of the table, you're going to calculate the kinetic energy the ball has right before it runs off the edge of the table. So the kinetic energy the ball has right at this point, as I've tried to show with this arrow, the kinetic energy at this point is calculated by simply taking 1/2 mv squared. The m is going to be in kilograms, the v is going to be in meters per second. This velocity that you're plugging in is the velocity the ball has right before it runs off the edge of the table. Now you're going to notice that your kinetic energy should be less than your gravitational potential energy that you started off with. If it was a frictionless track, where you're not losing any energy due to the work done by friction, then the potential energy you started off with will be the same as the kinetic energy right at the end of the track. However, this is not a frictionless track. Friction does exist, and it's slowing your ball down. It's not letting it go as fast as it could. So there is going to be a difference between the energies you started off with and the energy you end up with. So the potential energy that you started off with, mgh, should be a larger value than the kinetic energy. So you have to be very precise. If yours don't come out, if your kinetic energy isn't less than your potential energy, redo the experiment and verify everything to make sure that you're measuring everything correctly and you're plugging it into your calculator correctly. Your kinetic energy hopefully will come out to be less than your potential energy. So if you take the difference between the two energies, you're going to find out how much energy was lost to the environment, and that's directly related to the work being done by friction, because when friction does work on you, energy is being lost to the environment in the form of thermal energy or wave energy. Thermal energy basically is heat that's being created by the force of friction, and wave energy is basically vibrations that are traveling through the track when the ball is rolling through the track. But anyways, you're losing energy to the environment, and that's because of the work being done on the ball by friction. Now that you have the work being done by the force of friction, you can also calculate what the force of friction is by knowing how far the ball traveled on the track. So you know the distance of the ball, and you can go ahead and use that to find out the force of friction that was acting on the ball. So this is a different way to calculate the force of friction. In chapters 1 through 5, I showed you a few other ways to calculate the force of friction. In this activity, you're finding the force of friction using ideas from chapter 6, because you're going to use that to find the coefficient of friction also. So now that you have the work done by friction, you set it equals to force times displacement, because that's the equation for work. And the d in this equation is the distance of the track that you measured before you released the ball. So the d over here is the distance of the track right here, this distance, the distance in red. Okay, so it's going to be very easy once you know the left side of the equation, because you've calculated it up here. And you're going to divide it by the distance to find out the force of friction. So the d should be in meters. The work done by friction is in joules. So when you divide the joules by the meters, you're going to come out for the force of friction to be in newtons. So now that you know the force of friction, I want you to find the coefficient of friction, and that's not very difficult to do because you know how to calculate the coefficient of friction. I'll show it to you on the next slide. All you're going to do is now take the force of friction divided by the normal force, and that's going to give you the coefficient of friction. What is the normal force? Well, the normal force is the force that's acting on the ball when the ball is sitting in the track. So I'm just drawing a small section of the track. When the ball is sitting in the track, the force of gravity is pushing the ball down. And if the ball doesn't go down through the track, that means the track is strong enough and the table is strong enough to prevent the ball from going down. So that means the table and the track are exerting a force upwards. We call that the force, the normal force, the force that's exerted by the surface on a ball to keep it in static equilibrium, to keep it in place. So the simplest way to look at this is just to treat the ball as if it's just sitting in place. However, keep in mind, in Chapter 5, when we talk about vertical circular motion, we showed how the normal force changes when a ball is going through a vertical circle. And you may have multiple vertical circles in your track. The way I've drawn it, I have 2 vertical circles. So the normal force does change as the ball is going through the vertical circle. What we're doing over here is we're just trying to find the average normal force. So we're just treating it as the ball is sitting at rest. So it's a close approximation to determine the coefficient of friction. So your force of friction will be in newtons, your normal force will be in newtons. You divide the two, you're going to get the coefficient of friction. Hopefully you'll get a number between 0 and 1. Remember, the coefficient of friction is a unitless number. It has no units, it's just a ratio. It tells you how rough or smooth a surface is. The closer the number is to 0, the smoother the surface. The closer the number to 1, the rougher the surface. And you're calculating the coefficient of friction for the track that's being used.